Hi, this is Dane Quinn from the University of Akron, and today I'd like to give you a video lecture on the use of coordinates, and in particular, how different choices of coordinates can really simplify the resulting equations of motion that we get for mechanical systems. Well, let's start off and do this in the context of an example. Here on the right, we have a block of mass m that is free to slide on this inclined frictionless surface. Right, so the surface is at an angle of phi, and then it's connected by two springs, different spring constants, K1, K2, corresponding unstretched lengths L1 and L2, and a linear damper. I've given lots of dimensions here. In particular, the width of the block is W, and the total distance of this little channel is D. So again, we want to determine the equations of motion for this system. To start off, we'll think about what's going on a little bit. So if you look, this block is constrained to move only in one dimension, right? So it's constrained to move along the surface. As a result, we only need one coordinate to describe the configuration of the system, namely where the block is. We have lots of different choices, and we'll talk about a number of those in this lecture. But the important thing here is that this is a single degree of freedom system. So ultimately, we only need one coordinate to describe what's going on. Now, the next thing I want to think about are the forces that lead to motion in this problem. So if I look at this block and ask, what kinds of things are happening? Well, we have force due to gravity, right? That certainly acts on the system. All right, we've denoted the gravitational constant G here. We have forces from these springs. Those definitely act on the block. We have a force due to the damper. And then finally, right, we have a normal force from the surface. That essentially maintains contact between the inclined slope and the block. So really what we want to do first is just kind of identify those forces on our force diagram. So gravity acts in the vertical direction, right? So we'll say it's there. These springs, right, we have one that's here, right? We have one acting on the right. We have a damping force, and then the normal force. And of course, the normal force acts perpendicular to the surface. Let's go ahead and label these. This will be the force due to gravity. The normal force we'll call N. The two spring forces we'll say are F1 and F2, right, corresponding to K1 and K2. And then Fd will be the force due to damping. Now, again, before we jump into this, we want to think about how we'd like to set the problem up. And notice that we can actually define multiple coordinates can be used to specify the motion and the different forces. Right, so multiple coordinates. And when we talk about what should we define, really it's what's natural. So if you look at the force in spring 1, for example, right, the natural coordinate is going to be the stretch in spring 1. Spring 2, well, that's going to be the stretch in spring 2. So now let's go ahead and define those. We'll start off with coordinates and directions. Here we will identify the horizontal and vertical direction, I and j. And then noting that the surface is inclined, right, we'll define the direction along the surface as E1 and the direction perpendicular to the surface as E2. And of course, these are related by this angle phi that represents the inclination of the surface. So here the motion is only in the E1 direction, while gravity is in the J direction, for example. These forces are also in the E1 direction. This normal force, that's going to be in the E2 direction. Right? So most of these forces are really naturally expressed in the E1 and E2 direction. So that's what we're ultimately going to do. Now, in terms of these forces, again, the force in spring 1 is related to the stretch in spring 1. Right? So here, let's define that as X, while the force in spring 2 is naturally related to the stretch in spring 2. So that we'll define as Y. For the motion, we want to know the position of this block. So let's put a point B down here in the corner. We want to know the position of B with respect to some point fixed in the ground. Right? So we'll say that's O. So really what we're interested in is this vector. Right? So here, the position of the block is B with respect to O. In terms of the coordinates that we've defined, we can actually use a number of different coordinates, right? But let's use X. That seems to be the easiest at the moment, right? So this position vector is L1, the unstretched length of the spring, plus X, our stretch in the spring, in the E1 direction. So we've gotten, two coordinates, X and Y. And as we said before, those two are dependent on one another. If I know one of these, then I can tell you where the block is. So that brings us to our next step, which is to identify the constraint between X and Y. So again, here I have our picture, and I've gone ahead and labeled the coordinates X and Y, as well as these direction vectors. So to identify this constraint, we'll basically use the position of B with respect to O. Right? On the previous slide, we said that was equal to L1 plus X in the E1 direction. But we could also write that in terms of Y. Right? So essentially, I could start at O, go all the way over to the far end of the wall, and remember that is D, and then I could move back to B, right? So I would move back by the unstretched length of spring 2. I'd move back by Y, because here Y is defined positive to the left, and then I'd move back by this distance W, which was the width of the block. So comparing this, we see that L1 plus X is equal to all this stuff over here. Right? So in particular, a little bit of algebra, Y is equal to D minus L1 plus L2 plus W minus X. So if you know X, you can find Y, or if you knew Y, you could find X here. Lastly, for the kinematics, we will make use of these different directions, right? So let's go ahead and relate I and J and E1 and E2. So I, for example, in terms of E1 and E2, is cosine of phi in the E1 direction plus sine of phi in the E2 direction. Right? So again, if we want to go from here to there, we go out by cosine in the E1 direction, and then we go up by sine in the E2 direction. Likewise, J, we would see is minus sine in the E1 direction and cosine in the E2 direction. Of course, we can also do this for E1 and E2 in terms of sine, or in terms of I and J. And with that, we would find E1 is cosine I minus sine J. E2 is sine I plus cosine J. Maybe you want to pause this video and work some of this out. Work out these direction transformations, right? Make sure you understand this constraint equation, right? There's nothing wrong with pausing this and doing a little bit of work on the side. The last thing we'll need for this section of our analysis, kinematics, is the acceleration, right? So the acceleration of the block, well, that's the second derivative of position. And the position vector was r of b with respect to O. So let's use x here. If I take two derivatives of this expression, I simply get x double dot in the E1 direction. So again, we have the acceleration in terms of the coordinates. We have the constraints in terms of the coordinates, and we have the relationship between the direction vectors. So this was kind of step 2, right? Step 1 is always define coordinates and directions. Step 2 is look at the kinematics. And then moving on to step 3, we want to take those forces that we identified previously, right? So these forces that act on the block. And again, we did this in a separate step just to kind of make sure that we had a clear understanding of the forces that were influencing motion. So once we figure out that those forces are, kind of there, now we'll define them in terms of the coordinates and directions that we defined in step 1. So let's go through and do this. Gravity is fairly straightforward. That's minus mg in the j direction. This was the normal force. Now, I have no idea what the magnitude of the normal force is, but I do know that it's in the E2 direction, right? So I'll just give it some unknown magnitude, in the E2 direction. Now, you may be looking at this and go, I can figure this out, right? And you might be able to. In the E2 direction, the forces have to balance, right? So some component of the weight has to balance out this normal force. Again, you can do all this in your head, but I would urge you not to, because that actually comes from applying the equations of motion, right? Ultimately, I'll just go ahead and tell you, we'll find that n is equal to mg cosine of phi, which is maybe what you would have guessed anyway, but it's going to come out naturally from the equations of motion. I would urge you not to try to jump ahead in this process. Go ahead and define coordinates, define directions, do all this, apply the equations of motion, and then we'll solve for things like the unknown normal force, right? We don't need to do that ahead of time. Now we have the forces due to the springs and the damper. So let's look at K1 first. Spring 1, well, that's going to be minus K1, and the stretch was, of course, x, and that's in the E2 direction. Here, because y was defined positive in the minus E1 direction, this force is going to be K2 y in the plus E1 direction. Finally, the damping force, dampers are proportional to the velocity across them, and x does a good job of measuring that, right? So let's write this as minus b x dot in the E1 direction. Again, here we define the forces in terms of the coordinates and directions. That we defined earlier. And once again, my recommendation is don't try to solve for the unknown forces. Until we actually write down the equations of motion. Right? Just wait, be patient. Now, you might say, well, yeah, but over here, you've got, for example, K2 times y in the E1 direction, right? I don't know this force, yet you're writing it down. And to that, I would say, well, not really, because I don't know what y is. what I'm doing here is I'm relating this unknown force in terms of an unknown coordinate. So I'm not really solving for this force, right? All I'm doing is using the constitutive law for a spring that we know to be true, right? So solving for this normal force kind of in your head is very different than relating this unknown force to an unknown displacement through a constitutive law. So now we come to this all-important equations of motion step. And here we'll use linear momentum balance on the block. So of course that's sum of the forces equals mass times acceleration. And because we've done all the work ahead of time, really at this point, all we're doing is just kind of writing down stuff that we've already defined. I think that's one of the nice things about this way of working through modeling is that really all of the work is done in the kinematics and free body diagram step. Now, equations of motion, we're just taking all that and kind of putting it in the right spot, right? So let's go back and look. We have all of these forces, right? So, okay, we'll just write them all down. There was the spring force acting on spring 1, right? We had the damping force. That was B x dot in the E1 direction. We had the other spring, right? So that's K2 times Y in the E1 direction. Then we had a normal force, N, in the E2 direction. And finally, we had the weight, minus mg, in the J direction. Again, I just looked at these forces and wrote them all down, right? Here they all are. Here they are again. And of course, this is going to be equal to the mass times the acceleration of the block, which we have already defined as x double dot in the E1 direction. Okay, so look, I got a bunch of stuff. And at this point, I want to go and write this equation in terms of two perpendicular directions. I can choose any two. I could choose I and j, but if you notice, most of these terms are in terms of E1 and E2. There's only one term that's written in the I and j directions. So it's much simpler to take this one term and write it in terms of E1 and E2 than it is to try to take all of these terms and write them in terms of I and j. So let me just remind you what j was. J here is minus sine in the E1 direction plus cosine in the E2 direction. So when I come along, I can identify everything in the E1 direction. Well, I get minus k1x. Here I have minus b x dot. I have plus k2 times y. This is in the E2 direction, so there's no E1 component. For the weight, we have a component that looks like mg sine of phi. Remember, phi is the inclination angle. And those are all the terms in the E1 direction over on the left. In the E2 direction, I have n minus mg cosine of phi. E2. And this is equal to mx double dot in the E1 direction. And I'll just put here that there's nothing in the E2 direction. So we can take the E1 components and we can take the E2 components. For E1, we have mx double dot plus k1x plus b x dot minus k2 times y equals mg sine of phi. So I've rearranged things a little bit here. Now, in the E2 direction, we find that n is equal to mg cosine of phi, right? Because this term has to vanish. Well, okay, that's what we had kind of thought it was going to be. But again, it comes from the equations of motion. It doesn't come from... So again, it comes from the equations of motion. We don't have to kind of quote-unquote figure this out in our head, right? It just naturally arises from applying linear momentum balance. So now let's look back at the E1 direction. I have terms that depend on x, and I also have terms that depend on y, but y and x are related. So let's go and write this equation only in terms of x, right? Let's recall that y is equal to d minus L1 plus L2 plus w minus x. So as a result, finally, this equation of motion is mx double dot plus bx dot. I'll put the damping next. I'm going to put the stiffness terms next. So that's going to be K1, and then we'll have a K2 times x. And then on the right-hand side, we have mg sine of phi. And I also have a piece from this constraint equation, right? So this K2 times this term becomes K2 d minus L1 plus L2 plus w. And this is the equation of motion for this block in terms of x. Well, if I want to solve this, I'll have a particular solution and a homogeneous solution because, of course, the right-hand side is the forcing. And here, forcing implies the forcing on the equation of motion. And notice that that's constant. Right, so we can say mg sine of phi plus K2 times d minus L1 plus L2 plus w is some constant. So I'd expect that the particular solution has a constant piece in it. And then we'd have the homogeneous solution that, as we've seen, would be used to determine the response to specific initial conditions. If I look at this, I have two pieces here. This first piece, mg sine, is due to gravity. And this second piece is really due to the geometry of the system. Let's go back and look at that picture again. You know, if we think about what would influence the static position of this block, well, one of those things is the geometry, right? The unstretched length of the springs, the width of the block, the width of this whole channel. That geometry would come into essentially where this block would come to rest. And then there'd be a second effect from gravity. So gravity tends to move the block down the plane, right? So really, those two things, the gravitational load and the geometry, combine to influence the static equilibrium position. And that's exactly what we see here, right? There's a term due to gravity, and there's a term due to the geometry. So now going back to this equation, solving for the static equilibrium position essentially is this spring term, the force in the spring, in the two springs, balancing out this stuff on the right, right? And so we would find that the equilibrium position would be mg sine, and then this term due to the geometry d minus L1 and L2 and W, all divided by K1 plus K2. So again, this particular solution represents static equilibrium for the system. Of course, if we wanted to solve for specific initial conditions, then we'd go back and we would solve the homogeneous solution. But before we do that, now let's look at a change of coordinates. Different coordinates really can simplify the resulting equations of motion. Previously, we developed the equations of motion in terms of x, essentially the stretch in spring 1. But now let's look what happens if we change coordinates. Let's measure from static equilibrium. So we want to change coordinates so that x of t is the static displacement plus some new variable, which we'll call z. If we go in and look at the figure here, maybe the static displacement is this length. Right, so that's how much it stretches under the geometry and the gravitational load. And then we'll measure the resulting displacement from there with this coordinate z. Looking at these two, we see that now the position of the block with respect to O is L1 plus the static displacement plus z in the E1 direction. In addition, right, taking a derivative of the left-hand side, we get x dot, and taking the derivative of the right-hand side, static displacement is constant, so its derivative is 0, and we're just left with z dot. Likewise, x double dot is equal to z double dot. Looking at the original equation of motion that we had in terms of x, we saw that m x double dot plus b x dot, and then k1 plus k2 times x was mg sine, and k2 d minus L1 and L2 and W. So when I make this transformation, over on the left-hand side, I have m z double dot, right, because x double dot is z double dot. I have b times z dot, and then I have k1 plus k2 times x. Well, that's x equilibrium, the static displacement, plus z. And then we still have the right-hand side, mg sine plus k2 d minus all this other stuff. Right now, this doesn't look like any real advantage, except noting that the equilibrium displacement was defined as shown here. We see that k1 plus k2 times x equilibrium, well, the k1 plus k2s cancel out, and we're simply left with mg sine plus k2 d minus all this other stuff, which is exactly what is on the right-hand side. So really, by measuring from static equilibrium, this term pops up on the left-hand side because it's k1 plus k2 times the equilibrium displacement. And then that actually will cancel out what's on the right-hand side. This was, in fact, how the equilibrium position was chosen. So at the end of this, we end up with mz double dot plus b times z dot plus k1 plus k2 times z equals 0. So this is kind of interesting, right? It's certainly nice because before we had this huge piece in green over on the right-hand side that had some influence due to gravity and the geometry, and if we measure from static equilibrium, then all of that's gone. You know, essentially, this is equivalent to a system with no gravity, g is equal to 0, and no geometry. So all the unstretched lengths, all of the widths, all of that stuff is set equal to 0. So if I had this system with no gravity and none of these geometrical lengths, right, these are the equations of motion that we would get. Really, these constant terms they specify the equilibrium position or the static position, but do not influence the dynamics. So all the time-dependent behavior is encapsulated in this equation in and of itself. One important consequence of this is when measured from static equilibrium, so we have to go and calculate the static equilibrium position and then choose coordinates relative to that. But when we do that, these constant forcing terms are eliminated. So they don't affect the dynamic equations of motion. Oftentimes, when we're actually going through modeling, I will give you problems that, you know, maybe there's no mention of gravity. Right? There's no mention of unstretched lengths of springs, and there's no mention of the width of the block like there is in this problem. And there, you can assume that you're just going to measure from static equilibrium, right? So all those effects, which are important when determining the static position, are essentially neglected. Finally, let's look at the response parameters of this system. So again, here we have this equation of motion as measured from static equilibrium. Right? We see that the natural frequency is defined as this, effectively the coefficient in front of the position. So here that's K1 plus K2 divided by, you know, what's in front of the acceleration term, m. And likewise, the damping ratio for this system, zeta, is damping, B, 2 square root. Again, it's this total stiffness of the system, K1 plus K2 times m. And here, if we look at the response of the system, the initial conditions well, maybe those are given in terms of x. X is a nice physical measurement that we can make, right? It's possible to go into a lab and measure the stretch in the spring. Right? So here, x of 0, so the initial displacement is the equilibrium displacement, which we would find, plus the initial displacement of z. Likewise, x dot here is z dot. So if you're looking for initial conditions on z, it would be the initial stretch in the spring minus the equilibrium displacement. And the initial velocity of z dot, is just the same as the initial velocity in terms of x. And of course, the overall response is L1 plus x, or in terms of z, L1 plus the static displacement, again given here, plus then z of t, again in the E1 direction. So really, this lecture has derived equations of motion, and initially I did it including all of the geometry, right? So, for example, let's go back and look. The width of this channel, right? The width of the block, the unstretched lengths of the spring, right? So all of that was included. But what we find is that if we can measure from static equilibrium, all of those effects go away, right? So the acceleration due to gravity, g, right, doesn't influence the dynamic response. The geometry of the system, right, all of these parameters, they do not influence the dynamic response. The dynamic response of the system really only depends on the mass, the damping, and the stiffness. So that's it. We'll do some more examples, and we'll emphasize different things in coming lectures, right? But this is a good starting point for really looking at how different choices of coordinates can influence the resulting equations of motion that you get. Of course, I will say that regardless of the coordinates that you choose, you can solve this problem, right? And you can predict the response of the system. It's just that some coordinates tend to be more convenient than others. So that's it. Thanks so much, and we'll talk again.